Okay, now on to some other problems for other kinds of situations besides compound interest. Okay, in this example, we are told that the number n of bacteria in a flask after t hours obeys the function n of t equals 1000 times e to the 0.12t. Notice this is an exponential growth model. It's a number times e to a number times, and we're using t instead of x for the variable, t as in time, but that's pretty common. Okay, first question. How many bacteria are present at time t equals 0 hours? So if we're plugging in 0 for t, we're evaluating n of 0, which is 1000 times e to the 0.12 times 0. Okay, put that into your calculator, or actually this one we can do without a calculator, because 0.12 times 0 is 0. And e to the 0 is 1, because actually any number to the 0 power is 1. And then 1000 times 1 is 1000. So the answer to that question is 1000 bacteria. Notice that is the number out in front. The number out in front is the value of the function we get when we plug 0 in. So just before we go on to the next point, that's a good thing to keep in mind. That number out in front is the starting value or initial value of your exponential function. It's the value you start at time t equals 0. Okay, part B, how many bacteria are present after 5 hours? So now we're plugging 5 in for t, which means we're evaluating 1000 times e to the 0.12 times 5. And that comes out to be about 1822 bacteria. So that's just a straightforward plug into the formula and evaluate. But let me show you what that looks like on the calculator, just in case you're having trouble getting that number. Try this on your calculator. Make sure the number you get is 1822. But if it isn't, watch how I do it. So I'm putting in 1000 times e to the, in parentheses, 0.12 times 5, close parentheses. It shows up as 1822 point something, but I rounded it to the nearest whole number for the number of bacteria, and so it's 1822. Now, on to part C. When will the number of bacteria reach 2000? When means what time, what t, will the number of bacteria, will n of t, be equal to 2000? So this is asking, what does t have to be before the value of this function, 1000 e to the 0.12 t, is equal to 2000? So that gives us an equation that we have to solve for t. Okay, so how do we solve this? Well, first thing let's get rid of the 1000 in front of the e part by dividing both sides of this equation by 1000. Then we get e to the 0.12 t equals, and 2000 divided by 1000 would just be 2. Now get rid of the e by ln'ing. The inverse of the exponential function is the natural log function. So take ln of both sides, and we get 0.12t equals the ln of 2. Now, how do we go from 0.12t to just plain t? Divide both sides by 0.12. We get t equals ln of 2 divided by 0.12, and that comes out to be 5.776 something. So the answer is about 5.8 hours. Last part, how long will it take for the number of bacteria to triple? So again, it's asking us to find how long, what time, t, for the number of bacteria to triple. And remember, we started with 1,000. That was the initial value at time t equals 0. So for the number of bacteria to triple means that it would reach 3 times that amount, 3,000. So we want to know what t makes 1,000 times e to the 0.12 t equal to 3,000. So we're setting that equal to 3,000 and solving for t. Same steps that we go through. Divide both sides by 1,000. We get e to the 0.12 t equals 3. Take natural logarithms of both sides to undo the e, and 0.12 t equals the ln of 3. Divide both sides by 0.12, and we get t equals the ln of 3 divided by 0.12 is 9.155, and so on. So about 9.2 hours. So notice we started with 1,000. After about 5.8 hours, it had gone up to 2,000. After about 9.2 hours, it's gotten up to 3,000. It's growing faster, and the more bacteria we have, the faster it's going to grow. So it's not going to be too much longer before it reaches 4,000, and not too much longer after that before it reaches 5,000. So the more bacteria we have, the faster it grows. Okay, next example. A certain city had a population of 25,000 in the year 2000 and 30,000 people in the year 2010. Assume that the population follows an uninhibited exponential growth model. Now here it just says assume that. We're taking that as given. In the real world, sometimes that's an accurate assumption and often it's not. And the only way to tell is to actually look at the population over time, look at the pattern it follows from year to year to year, and see if it fits that kind of a pattern. See if the population, if you graph it over time, has that shape of a graph that looks like an exponential growth model. And even if it does, there's no guarantee that it will keep on following that kind of a model. But here, we're just going to assume that it does for at least the time period that we're dealing with here. So if we make that assumption, find a formula for the population t years since 2000. So if we're assuming that it follows an uninhibited exponential growth model, that means that the formula has this kind of a pattern to it. It's some number a times e to some other number b times the variable, x or t or whatever we want to use for the independent variable. Here we're talking about time, so we'll use t for the variable that the population depends on. Okay, now that number out in front, the a, that's our initial value. If we set things up so that t equals 0 in the year 2000, if we take that as our starting point and then t stands for how many years it's been since that starting point, then the year 2000 itself is the starting point where t is 0, and the population in that year where t is 0, that's our initial value. That's our starting population. So we can put that in for our initial value. That's the number in front. So P of t equals 25,000 times e to the bt. Then we have our other data point that 10 years after our starting point, when t is 10, the population is 30,000 people. So if you plug in 10 for t, what comes out should equal 30,000. So that means that P of 10, 25,000 times e to the whatever b is times 10 should equal 30,000. Okay, that gives us an equation that we can use to work out what number b has to be. We can solve this equation to get a value for b. So to do that, first divide both sides of this equation by 25,000. Then we get e to the b times 10, or e to the 10b, equals 30,000 divided by 25,000, which if you actually divide that comes out to be 1.2. So now we have e to the 10b equals 1.2. You remember what we do to get rid of the e. To get the e out of the way, we take natural logs of both sides. So ln of e to the 10b would just be 10b. And then on the other side, we get ln of 1.2. And then to go from 10b to just b, well, b would be the ln of 1.2 divided by 10, which is approximately 0.018232. So now our formula is P of t equals 25,000 times e to that number for b, times t. Now here's a little hint. If you're doing this on your calculator, when we calculated the value of b, here's how I did it on the calculator. I put it in as the ln of 1.2 divided by 10, and the calculator told me that that is 0.01823215557. Now, if I don't want to worry about round-off error, I want to keep as many decimal places as the calculator can give me, and I don't want to have to keep typing in all these numbers. If I use that formula and answer further questions, what I can do is I can store that number in the calculator's memory. Now, exactly how that works depends on what model of calculator you're using. In this particular calculator, what I can do is I can push the button labeled STO for store. So that will store the answer that I got in one of the calculator's memories. Now I'm going to store it as B, just because that's the letter I was using. So I'm going to push the alpha button and then push the button that has a B above it in the same color that the alpha button is. So if I push that button that has a B above it, it shows up as a B. I hit enter, and now that number has been stored in the calculator's memory as B. From here on out, if I push alpha B, the calculator is going to give me that number as the value for B. Now that I have this formula, I can use it to answer questions like, what will the population be in the year 2040? So that would be 40 years after the year I was taking as my starting point. Remember, T stands for how many years it's been since the year 2000. So the year 2040 would be when T is 40. So if I plug 40 in for T, that's 25,000 times e to the b, that number, times 40. So here's how I would evaluate that on the calculator. Hey, calculator, tell me 25,000 times e to the, in parentheses, B, that number that I stored as B, that I could type in again, 0.01823215557, but I've already got it stored, so I can just ask the calculator for B times 40. Close the parentheses, hit enter, and it comes up as 51,840. So that's my answer. According to this model, in the year 2040, the population will have gotten up to 51,840. In what year was the population 20,000? Okay, this video is running a little long, so I'm going to pause here and come back in part 3 to give you the answer to that question. Come back in the next part and work through that and give you the answer. I guess it's actually part 4, but see you then.